Hi everyone, and this is Wen Lan from 78, and today I want to show a topic for EV, electric vehicle for electrification in vehicle industry. And so I will give you some simulation solutions by Ansys for EV powertrain in this presentation. And so if you have any question, please type in the QA panel and I will start my presentation now. And for start my presentation, I will give you some success story by using Ansys. And so Lucid Motors, I believe many people heard for this name. And Lucid is building its own new luxury class electric vehicle, which is designed to compete with the leaders in the high-end EV market. And so at Lucid, they were able to compress the design cycle by 50%. For example, from 6 to 7 years in traditional way and to 3 years, and largely using Ansys simulation. And so Lucid engineers extensively leverage Ansys multiphysics simulation software to improve the operation of most of the vehicle's subsystems. And so using Ansys engineers at Lucid will able to increase power density and energy efficiency of motor by 12%, and to reduce volume and weight of inverter housing by 50%, and increase the leg run by reducing the size of front inverter motor and HVAC and freeing some space for battery, and substantially increase the life of the battery by understanding the potential conditions that could degrade the electrode. And finally, minimize the drag through the aerodynamics simulation and increase range to 400 miles. Similarly, other organizations like GM, Ford, Porsche, Toyota, and A123 are benefiting using a multiphysics simulation from Ansys. And so I believe you are very interesting for this kind of powertrain solutions. And so to lead the EV market, organizations must meet key engineering goals, performance, safety, and cost. And for performance, one of the concerns the potential buyer is how far an electric vehicle can travel without a need of charging. And the goal is to reduce the range anxiety. Preferred range is over 400 miles, while today it is 60 to 300 miles for EV. And so improve battery life and make it comparable to vehicle life about 10 years. Today, battery warranty is about 7 to 8 years. And so for increasing battery and motor power density creates differentiator in terms of comfort, like reduced noise and vibration. And for safety topic, safety is the most important criteria for EV. Even a single battery fire could turn public opinion against electric mobility and setback to electric vehicle development. And vehicle and components needs to be tested against industry standards for compliance and reliability. And the switching device, like IGBT in inverter and DC converter, then leads to a ripple and over voltage. And this may lead to a value of dielectrics. And also the switching device result in emission, which we need to make sure is below regulatory standards. And sorry. And for cost issues, affordability is one of the factors for mass adoption. And the production cost of EV should be equivalent or lower than that of IC engine vehicle. 30 to 40% cost of EV is battery, and is expected to reduce battery cost minus to $100 per kilowatt per hour. And with increase in electronics, software development cost and time has increased, and there is need to improve development productivity and reduce manual error. And so using the Ansys solutions, multiple organizations have achieved positive impact in areas of performance, safety, and cost. And for example, simulation enabled Lucy engineers to increase the power density and energy efficiency of traction motor by 12%. And leverage simulation Subaru were able to generate such a highly reliable code that manual review was no longer required, resulting in a great reduction of tests. The amount of automation increased to 95%. And the NEVs, the National Electric Vehicles Sweden team expects to achieve 30% productivity gain compared to the usual tool set. And SCADE model, SCADE is one of Ansys products, and allows them to detect errors in their specification early in the design process instead of during integration testing for BMS development. And so for the EV powertrain, there are four I think it is a unit or system in these critical areas. And the first one is battery and battery management systems. And then the second is electric machines. And the third one is power electronics, like inverter and DC-DC converter or other power electronics device. And the final is the powertrain system integration. So we are ensuring tight connectivity among our customers, our partners, colleagues, and other thought leaders. And the first one topic I will show battery and battery management subsistence solution. And for this kind of battery module, they will have the multi-physics and analyze requirements. And from the sales design team, they have to solve the electrochemical problem in the electrode performance. And for the battery module or battery pack, we should concern the thermal and mechanical issue, like temperature or mechanical is for drop test or shock test and so on. And if we want to combine or integrate the BMS and the battery pack, and we should have the software in BMS and have system issue for strategy to control the battery pack. And also, if our battery and BMS system is on the vehicle, and the EMI EMC issue is required that we have to meet the regular in or standards. And so this kind of topics is for more power density and more life cycle. And in the first one, from cell level, electrode performance is very important. And so how to increase the power density, to increase the battery life, and electro simulation in CFD. And we can use CFD to simulate the charge and discharge phenomenon. And for a different electrode design, and we can do some sensitivity analysis, and like the presentation in this page, the paper is for the electrode design and to do the discharge performance analysis. And so there have some experiment results to compare with the analyzed results. And so in a battery pack or modules, thermal management is for confirm the battery safety and battery life. And so if we use a CFD, Ansys CFD, Ansys Fluent, and we can simulate the battery cell to cell and how the heat will transfer to another cell, and how the and the temperature distribution in the whole module or pack. And we can use the mass capability in Ansys, and we can simplify the mesh process and to estimate how we analyze this battery pack. And because of the heat from battery is from the is caused by electrochemical. So we can use because Ansys have the many powerful for cooperation with different physics. So we can do the thermal analysis from the electrochemical analysis, and we can also do the thermal and chemical simulation. And in a battery module and pack, another issue is for thermal is thermal abuse and runaway mitigation. And because if our battery cell have only one or a few have some problem, maybe crack or it's not a normal product, then maybe in the battery pack you will have this cell overheating and to effect to other battery cells. And so So we should have to do the limit operation like over voltage or current. And so if we do this kind of test, we can use CFD to analyze the heat transfer from cell to cell, and we can use this to find a heat points to avoid the very temperature type runaway mitigation phenomenon, and this can very effective to do the battery heat thermal management and to reduce the risk of the thermal abuse. And in the battery pack level, it's very hard to put the whole pack and cell into FEA software because if the pack have many cells in this pack, and these battery cells and the case are all have to do the mesh setting and do the mesh for CFD simulation. But Ansys can give us the solution is to using the ECM model integrate with FEA. And so we can use the FEA model to simulate the battery cells thermal results, and use this result we can create the electrical ECM model. And ECM model means equivalent circuit model, and so we can do the integration, build one ECM model for a cell, and to combine the all cells and do the connection or link into the one battery pack by using Twin Builder or simpler software. And so this kind of software gives us the circuit model building capability, and so we can use this Twin Builder to do the quickly simulation by check the thermal management issue, like if we use air cooled or use liquid cooled. And so we can use this to minimize our compute time and to do the optimization of battery pack design. And also in liquid cooling, we can also use the ECM model. And besides ECM model, another capability in Twin Builder is RN model, and RN means reduce order model. And it means not only battery cells, but also the environment or the but also busbar environments, and we can build our model into Twin Builder. And so use this kind of simulation model, we can do the digital twin and to complete the real-time simulation and monitor the battery performance and to expect the battery model's fault or life. And for the EV battery, besides power density and life issues, the most important issue we have to care about is safety. And so for battery, the world have many kinds of regular is about battery safety, and by using Ansys, and we can simulate the battery drop impact, thermal shock, and also nail penetration. And for the vibration on the electric vehicle, the battery case must to afford a continuous vibration, and this kind of vibration have some patterns in the regular, and so these are all to be confirmed when we sell our battery products. And so before the battery test, and we can use software to simulate this kind of simulation to reduce the test time, and we can reduce the design. Also, we can reduce the design iteration to reduce the development time. And also in EV systems, because there doesn't have a complete and stable ground in the car, and so systems EMI EMC will be produced because of this issue. And so by using system simulation, we can focus on emission source to be simulation, such like a BNS busbar or switching device. And so that we can simulate the common mode noise and differential mode noise, and by using systems model simulation. And for BMS system development, because we have to build some control strategy in our BMS software, and now many EV control system is all using MBD design to build up the software architecture. And MBD means model-based design. And so it's same as the BMS software and control strategy. And to do the MBD design, and first we use the block diagram to do the control strategy, and then after the heel or seal testing, and we will transfer the block diagram model to C code or others program language. And so for make sure the MBD model to C code is very it has enough reliability, and Ansys SCADA give us the solution, and this kind of solution have passed the ISO 26262 certification, and by it's kind of the design tool certification in ISO 26262, and so it gives us one-to-one C code transfer by MBD, and if in traditional, I think many kind of engineers is using MATLAB Simlinker to transfer the C code or to do the control stage strategy, but it have some risk, and if it is not not the one-to-one convert model in Simlink, and so it takes it's not very reliable by using Simlink to transfer the C code to build the EB's control strategy. And so because SCADA are using in rail vehicle like subway, high-speed rail operation system, so you have very widely used in this kind of application. So SCADA is a very convenient and very reliability product by design and building the BNS coding. And so also BNS system can using Twin Builder to build a real-time simulation model, and not only to integrate Twin Builder and SCADA, but also we can using test data and simulation data to build a role model, and so we can confirm the battery performance output for different BNS control strategy and architecture. And also we can dynamically identify overheating and protection behaviors. And for not only battery system, we can also use Twin Builder to build the for electric vehicle propulsion, and to integrate battery, inverter, and the motor. And this we call the tri-electric system. And so this whole system, we can all building the real-time model in Twin Builder, and so we can do the very fast system validation, like the functional safety verification, like ISO 26262, and also the dangerous test in other regular, and so it can improve our product design cycle in whole battery design. And so from cell to whole battery system, Ansys give us the complete simulation tool for accelerating our design process. And so here I will give you the solution product matrix, and this could let you to check that which kind of tool or package is good for or suitable for you. And so you can check that if you are cell level or page level or system level. And so you can check this table to find out the suitable tool package. And second is the electric machine design. And the electric vehicle machine, we call it EV traction motor. It's also the multi-physics products from EV electromagnetic design and to thermal structure and also the control. And this is all we should care about in motor design. And so this is one kind of the motor design process I used in my previous job. And so from design target, because EV had the different design targets we should care about, like the peak power, rated power, rated torque, and also we should have the NVH criteria like cooking torque and torque ripple. And so after design the target, and we should do the concept design. And in this step, and we should choose which kind of motor we should use. In vehicle application, most people like to use a PM motor and or the synchronized PM system synchronized iron motor. And the motor sizing is have to meet the car engine space in the EV. And so we also have to do some concept design to meet the space in the car. And the third space, we should do the detailed EM design and to check the torque ripple, flux density, and also we should do the voltage inputs and optimization issue. And next, we should mapping or transfer the EM design result like loss, force, or others, and we should check the motor thermal issue or stress issue like NVH, natural frequency, or temperature distribution to check the peak powers continuous time. And finally, for the different control strategy and different inverter architecture, and we should do the total simulation to do the inverter and motor total simulation. And in system analysis, we should use the also role model in Builder to do the simulation. And so for the Ansys model design flow, and we should have to use ModelCAD in concept design and make sure 2D and 3D can afford the design, the detailed EM design. And also we should use mechanical and CFD to do the thermal and structural analysis. and team builder. Also, we can do the system analysis. So Ansys gives us the very complete design platform for the EV motor. And so in the concept design and specification, and ModelCAD will have 4 modules. It makes thermal, mechanical, and lab. And this kind of module can quickly give us some results for different physics domain results. And so we can use image to check the torque and efficiency, and we can use the module to check the motor temperature distribution. And also we can use mechanical to check the rotor bridge strength in this module. And lab module, we can check the efficiency made, and we can we consult for operation points. And so this slide represents Ansys mixture solutions, and it's for the advanced magnetic analysis. Like some issues we will care about. First, for example, motor skill, because for reduce the cooking torque and torque ripple, we all usually use the skill of rotor or stator geometry along the Z-axis. And second is magnetostriction. Is property of ferromagnetic materials, which cause them to expand or contract in response to a magnetic field. And third, we concern the demagnetization. When the temperature of the magnet crosses the threshold point, it may start losing its magnetic properties. And so there are many issues or details results we should care about by Maxwell. And also we can use both ModelCAD and Maxwell to simulate the motor efficiency made or torque speed curve. And also we can do the IDIQ, LDLQ map in ModelCAD and Maxwell. And what's the difference is between these two kind of tools is the accuracy. Because ModelCAD is very speed calculation in this kind of map, and so if you compare it with the experimental results, and Maxwell will have close to the experiment result than ModelCAD. And in the thermal management, we can use CFD co-simulation with Maxwell, and we can transfer the loss result into CFD, and after simulation, CFD will give temperature distribution into Maxwell. And to do the 3 to 5 iteration, we will get the more accuracy result by temperature distribution in this motor. And in CFD, they have a very fast pre-processing, like the new machine module watertight, and so we can get the more effective compute tool. And for the MBH and structural integrity issue, we can also start from Maxwell to give the magnetic force to mechanical. And we can use mechanical to analyze the vibration and noise. And also we can use the VR experience sound, and it can give us the real sound quality we can hear in the computer. And in the others issue we care about is it's kind of to do the optimization of the motor design, because for EV motor we are concerned the power density and efficiency and cost, and so if we want to do the high performance motor, and so optimization method is suitable to do the high quality model design. And so Subsistence will be the best tools to do the connection with Ansys mechanical, mixture, and fluent. And so to do the optimization, we can get maybe some 2% higher efficiency, or reduce the 10% motor weight, or to use less magnet by 20% to reduce the motor cost. And so this will be the very good solution to do the more high power density and low cost products. And at this stage, we develop a motor run model which has the motor performance in the form of lookup table with having nonlinear physics behavior intact. And so a role model can then be coupled with power electronics to simulate the entire electrical drive system, or we can integrate with a hardware system to basically carry out hill simulations. And so I will give you some real case in Taiwan, and this is one of the traction motor for event. And this kind of motor we complete the electromagnetic and thermal consummation in this case. And so I finished the Maxwell 3D analyze, and to give the EM loss to Ansys Fluent by Ansys Workbench platform. And so as you can see, we can link the geometry model and also EM loss into Ansys Fluent, and so to do the EM thermal consummation. And we also constantly temperature test in this kind of even traction motor, and so we check the EM loss, like rotor loss, stator loss, and winding loss, and to do the validation with simulation results. And so after we check out this kind of result, we renew the loss model and to do the confirmation again. And so we can choose easy to do the confirmation by this kind of process. And so we finish the workbench linkage between mixture and fluent, and we can open the fluent to choose the EM mapping, and the EM loss will mapping to the fluent automatically. And finally, we just choose the model to do the CFD settings, and we can finish the confirmation. And this is another issue for the NVH problem. And same of the model. This is the same model for the same event, and we do the log force analysis to check the force distribution of time, and so we can build up the force distribution plot to compare with our new model design. And because this kind of design, we had this problem in real vehicle at the 20 kph to and the 50 kph vehicle speed. And so to solve this problem, we have to change our motor design to like a slot pole ratio. And because we find out the NVH is caused by the wrong slot pole ratio design, and so we set up 3 different slot pole ratio, and to do the force distribution by Ansys mixture. And finally, we choose the good design results for a better mode number and LCM number. And so finally, our rear car test to compare the first model and generation 2 motor, the image problem are will solve finally. And so this is also the solution product matrix, and you can get a reference. And so if you are only the motor product company, and maybe you can use Ansys Motorcade, Mixture, and also Mechanical and Ansys Fluent. And if you are the EV or the system company, and you should have to do some kind of build model to do the system simulation. And the third part is power electronics design and development overview. And for power electronics design, we also have to check the electrical by circuit design or PCB SIPI question or EMI issue. And also, if we have the model case and the IGBT product, and so we have to check the mechanical by its strength, and also to simulate the IGBT thermal issue. And also we have the software in the control board. So we should have to use like scale to do the MBD design. And so when higher power densities increased efficiency and ensure EMI and thermal issue ensue. Then starting with multi-domain circuit and system simulation is the place to start. And so for accurate semiconductor losses, controls, and abilities to improve models for magnetics and parasitics is imperative to enable a broader application range and reduce the test cycle for EMI, and also reduce the failure due to thermal stress, and to increase the competitive advantage. And so in the magnetic components, such as inductors and transformers, are source of heat and may cause thermal issues. So these components may take up space on our PCB layout because now we have many planar transformer and planar inductors on our PCB. And so these components, leakage inductance and other parasitics can cause electrical transients. And other magnetic components, such as cables and even the current distribution in bus bars or PCPs carrying larger currents, are also source of heat. And also EMI problem are caused by this bus bar. And so according for magnetic components, skin and proximity effects and parasitics will have the following benefits of increased power density and also reduced hot spots, operation below thermal limits. And to enhance the thermal performance, heat source in power electronics applications that can be cost of exceeding thermal limit include power semiconductors, which at higher and higher frequencies. As I know, maybe if you are using IGBT, and switching frequency is about 8,000 hertz to 12K hertz. And if you use more higher frequency switching, then maybe you are using silicon carbide or gallium nitride. And so you will have a higher frequency, in which you will have higher switching loss. You should care about, or other EMI issue will caused by this kind of higher frequency switching. And also power magnetic components such as inductors and transformers will have here heat source issue, and cables and bus bars carrying high current. So understanding well hotspots are located, and how to properly remove the heat from their enclosures by simulation. Have the following benefits. Is enhanced reliability and cost-effective thermal drive cycle testing, and reduce the thermal measurements. And to integration of controls with representative physics-based trend models is important to ensure that the embedded control are properly engineered, as well as helping to ensure system performance meet requirements. And in addition, generating qualified code, especially for safety critical application, has the following benefits. And it means we use scale to do the embedded design for the more quality C code or code generation. And so we can reduce the development time and cost through seamless certification flow and early verification and validation. And also it ensures safety of embedded software. And a switching frequency for power electronics application are pushed higher to meet increased power densities. Concerns with meeting conductor and radiate EMI standards becomes more difficult. And so including in simulation accurate power semiconductor model, frequency dependence characteristics, EMI ENC components libraries, and automatic and streamlined workflow have the following benefits. And one is early detection and mitigation of EMI ENC effects, and to do the weak point localization that cannot be determined by measurements. And we can also reduce the time and cost for tests by 20 to 40%. And also because we are design the EV products, so the reliability issue are very important than the 3C products like cell phone, computer, and notebook. And because in EV products, the safety is first priority in the designers who should be concerned. And so the failure of the PCB from thermal mechanical strength, shock, and vibration, and external environmental effects are costly problems, and are not easily solved with the traditional design build test break fix workflow. And so because if we want to check out the PCB reliability or its life cycle, it takes maybe a few months or few years to do the acceleration test. So to solve these problems, if we want to have a robust lifetime prediction through simulation, have the following to use Ansys dialog, then we will have the following benefits. The first one is to reduce costs associated with physics testing through virtual exploration and validation. And second is rapidly calculate PCB label time to various estimates for all components on the board. And if you import the e-cage to Ansys lock, and you can do the very fast simulation for in few minutes to finish the lifetime prediction, like thermal shock or some cycle. And so this chart also aligns the capabilities and applications we discussed in this presentation with specific Ansys products. And so if you want to learn more about these products, maybe you should refer this kind of website link. And finally, is for I will introduce the electrified powertrain system integration. And system integration of the electrified powertrain is the most critical part of your electrification journey. And you have different things in different regions to work with many suppliers to integrate all these major components and subsystems to have an eventual optimized system with consideration of trade-offs between performance, cost, and reliability. And so in order to achieve this in a more cost effective and timely manner than your competitors, a system integration environment dedicates for electrified powertrain is needed, where engineers can architect the system, integrate that critical components, and perform system integration with mission critical embedded software with consideration of functional safety to meet standards in the industry. And so typically, a top-down design process starts with the definition of power architecture, which describe which basic components are needed and how to interact. The goal at this level is to evaluate several architecture in the most efficient manner about the requirements. And even at this level, it requires input from multiple teams from different disciplines and partners from the supply chain. And the components of the electric powertrain can be considered on various levels of details. From functional descriptions run and to do the co-simulation. And based on the requirement variety layout organized in libraries and allow reusing the existing components. The work is facilitated by tailored templates and results to reduce the time needed to construct the system. And so through the ease of use of the interface, open formats, reuse of existing components and systems, where applicable the time needed to evaluate several and find the best suitable architecture within given boundary conditions can be significantly reduced, even half. And depending on where you are in the design process, you want to consider components model in different abstraction levels, then like low, medium, or high fidelity, respectively. And low fidelity fidelity means functions, vectors, or lookout tables. And the median stands for advanced model, such as a reduced order model from the field simulation or measurement. The high level of fidelity comes from the 3D field simulation or co-simulation. And so the goal is to intuitively manage all these models in libraries. And here the component to subsystem and to system integration paths is shown on the inverter example. And the powertrain systems, first is the power electronic inverter, which controls motion, quality, and power flow of the powertrain. And the inverter is a subsystem and itself consists of the other components and subsystems. An example of which being a magnetic transformer or filter. The same will apply for all other powertrain system components like battery system, motor, mechanical transmission, and so on. And creating a correct and certifiable software for your ECU is key for success. And starting from requirements, writing code, testing, and also performing all kinds of ENV activities can be a time-consuming task. And at the same time, there is a high risk of introducing errors in manual coding. And our solution is a model-based toolchain to describe safety criticals for software in combination with automatic code generation. And this drastically reduce the development time, and efficient development is enabled, and so risk is minimized for your successful safety software development. The well-known V-cycle is fully supported by the model-based toolchain. After modeling the system on the basis of system MI and or AutoSAR in an ISO 262 context, the software interface can be automatically synchronized to the model-based software design tool. At this level, the logic is implemented and easy to use. Graphical, sorry. Graphical front end, due to the at this level, the logic is implemented with an easy to use graphical front end. And so due to the use of predefined elements and various levels of tracking, it is ensured that only valid functionality is being created. And from here, the final application code is only a single mouse click away, and it's generated using a certified code generator. So the expensive and risky step of manual coding is history. Then on the right-hand side of the vehicle software testing and additional VMware activities are supported by our toolchain. Seamlessly integrate and certified test engine ensure quality of your software application. Moreover, further analysis such as MCDC coverage or formal verification, for instance, can be taken as safety relevant credits. And anytime all process steps are conducted with close bringing a reference to requirements for this course. Gateway to third-party requirements management tools is available. No matter which of these tools you choose, the intuitive use in the model-based toolchain is always the same and straightforward. And so, for example, the Volkswagen battery management group switched to this model based toolchain and gained an increase of core time of 43%. And so the outstanding result proves the advantages, capabilities of the end-to-end toolchain. Needless to say that automotive domain is fully supported. We are supported as soon as possible tool and AutoSAR support AutoSAR standard. Okay, yeah. In the domain of functional safety, it is essential to be compliant with the state-of-the-art standards and regulations. And increasing complexity of safety-related systems make it more difficult to achieve compliance with these standards. And traceability and consistency of the safety case is hard to be realized when you have multiple solutions that are not connected with each other. And safety and security have to work together in the future. As an insecure system is not safe, automated driving systems put more responsibility for safety on the manufacturer and its suppliers. And the key to address this increased effort is to work with model-based integrated solutions. And they allow the engineers to keep track with the complexity while being guided through the safety case without losing the consistency. Looking at models, it is possible to add safety or security-related attributed and overcome conflicts at a very early design phase, not after the product is launched, and avoid callbacks. And automatics reports allow the engineer to save time following the required documentation process. And reusable model templates allow engineers to start not always from the scratch, and variants can be developed much faster. And counting together traceability, consistency, automation, reuse, time-lapse creation, single source of information helps our customers to achieve and afford reduction of time to entitled markets up to 57%. With the increasing complexity of the safety resistant and integrated high performance solution is beneficial for additional cost saving and safe products. And so it's also the chart about the Ansys products to applications. And you can find this kind of matrix to check like which kind of solution you are interested, and you can search these products or contact us. And so finally, it's about some introduce for Ansys, and and Ansys is the leading the simulation market for 50 years, and Ansys integrate more and more simulation tools to do the very accuracy simulation by many applications like EV, 5G, and in the fan motor and so on. And so if you have any kind of question, or if you want to improve your work, your product, and to solve your problem with low cost, Ansys is to setting the gold standard for simulation solutions. And so this is the end of my presentation.